So far we've gone through a number of sorting algorithms, the simple versions that calls for unsophisticated, exhaustive brute force iterations. These are O of n square, right? So examples would be selection sort, bubble sort, or even insertion sorts. These are very time consuming as we went through analysis. And when n becomes large, right? The amount of time, right, becomes prohibitive, right, for any real-time application. So that's something that we wanted to avoid. Therefore, let's look into a couple of the other methods that are more advanced that involves much less iterations. So there are several algorithms out there that does this, namely merge sort, quick sort. At some point you can get into Redis. There's so many other algorithms that we can look at. Let's go through this other what we call n log n sort. And this example that we're going to go through is called merge sort. But before we get into it, let's kind of understand, what this sorting algorithm is. So this is the sorting algorithms that divides a list into two halves. Basically, it's a divide and conquer methods that recursively sorts it, basically each half, and then merges the sorted halves, right, to produce a sorted list. This is a recursive partitioning that basically continues until a list of one elements is reached, or as a list of one elements is already sorted. So this merge sort calls for, like I said, divide and conquer, and that basically says, fundamentally just cutting the list in half. If you would have a list of elements and you engage in some sort of n square, right, over n square, halving it, right, basically means I just want in the beginning I have this much. I wanted to half my problem space here, so I divided it into a left and right. So I would sort each of these partition using O of log, right, O of n square. So this O of n square calling for, and of course here that n is n divided by 2, right? So this is half n square, right? Half n square. So this is the left side and this is the right side. If I were to do that, so this is actually square, half the square. Then together, I get half n square. Now half n square is smaller, right, than obviously n square. And this is the idea of let's just maybe divide my entire problem space into kind of like binary sorts, right? You halving each problem space by half on the order of half each time you get down to the next tier. And this divide and conquer, as you can see here, is already giving you benefits, even though we're sticking to the same sorting algorithm, maybe insertions, right, for each of these half. But the benefit, as you can see here, is tremendous, right? But sorting half of it does not mean that we're done, right? Because you have to merge left and right together. So there is a cost associated with merging the two back together. But sometimes this merge, as we will see, this merge it's calls for O of n, which is really not that bad. So together, even if you just stick with the worst case unsophisticated sorting algorithms for each of the half, plus O over n, right, together is still much better, right, than O of n squared. So that is the whole thing, right, about this divide and conquer idea. But before we get into the merge sort, let's kind of look at kind of conceptually what this this divide and conquer really means. So the next part is the rationale for divide and conquer. As you can see here, let's say if we have 100 elements here and then we divide it in in half and sort them accordingly. The math here goes n is 100, n squared then is 10,000, right? If you cut it in half, then it's 50, right? Let's just assume that we're using the O of n square, right? Sorting efficiency here. So half of n square plus half of n square. This together is the merging, right? The merging part. This part together gives us basically right? Half of, actually, no, in this case, it's already computed, right? So on the bottom. But what about this 100? Well, this 100 is what I called, the merging algorithms, right? So when you sort half of it, like this part is already sorted, this part, you have to somehow merge them together, right? So basically doing a plus on this. And that is O of n, right? And because n is 50, actually, no, n is 100, O of n is 100, right? So this is the reason why you see 50 square plus 50 square plus 100. Total number of comparisons is 5100 as compared to 10,000s, right? As you can see, this divide and conquer is actually giving us benefits here. And in fact, if we stick with this idea, maybe we can do something, right, by bringing down the entire sorting algorithms using this divide and conquer method to O of what we call log n. Okay, so this is a huge savings there. So that's what actually O of n log n, not log n there, because we're not talking about binary source here. It's a divide and conquer using merge. Okay, so without further ado, let's look into the merging part. So we'll talk about the sorting algorithms later, okay? Because that involves recursions. But just the merge sort algorithm on a 30,000 foot view here, and then let's look at the merge of the two half, right, in the next couple of slides. Okay, so merge sort essentially says this: cut the array in half and sort the left half and sort the right half, right, and then merge the two. So that's basically it, right? It itself a sorting algorithms, right? We might as well sort the two halves. We can make the merge sort recursive scheme basically. If you know the beginning, right, the ending of your left and the beginning and ending of the right, you can basically write this one single sorting algorithms that in and of itself is recursive. There's a couple of base conditions that we need to set, right? Because when you get into recursions, notice that the very first one principle is that you have to have a base conditions, right? And the recursion itself could be expressed, right, into a general case. So sorting the left and half is already a general case. We just need the base case in order to ensure that right, our recursion bubbles up, right? At some point, you're gonna have to stop it, otherwise it will go into infinitive, and then you're gonna run out of memory. So cutting the problem space in half into left and right, sort them accordingly, and then merge them, right? So it's double sorting left, sorting right, plus a merge. All right, so let's go through the merge sort later. Let's study how we merge the two sorted half, right, into one sorted array. So this part is something that we're interested in. This one is the O of n, right, time. Let's look at the specific mechanisms from the high level. Into the next part, the merge sort summary. Okay, so this is what we were talking about earlier when we have a merge sort recursion that takes place. The first and last is the first index and the last index, right, of each respective sorting problem space. The number of elements that you have is last minus first plus one. This makes sense, right? Because size, right, is one elements over the last indexing, because array indexing, in this case we're using array, right, as an underlying buffer. Array indexing is always one less the size. So the size itself is actually the actual number of the diff, right, between the last and first and plus one, because we need to convert it into a size. So last minus first plus one, this is a plus, gives you the number of size. And of course, when you get into the base case, this base case is when you need to stop, right, recursing further. If the size is less than 2, meaning you have only 1 or 0 left, you don't want to merge sort, right? There's nothing to merge. If there's only one element, if there's no elements left, you don't want to merge sort either, right? So in this case, the recursion stops at the base case in this case. And the general case we already talked about, right? Cutting the array in half, right? However many elements you have, basically divided in half, right? Because we know the size. And then since we know the size, we know the beginning, basically the first and the last, right? You can abstract this and just come up with a generalized version of the left and right in terms of their first index and last index. And then we can merge the half into one sorted array. So let's look at the merge part. And then later on in a different clip, we're talking about merge sort, right? Okay, so this is the strategy for merging two sorted arrays. So let's look at perhaps, we have two sorted array already. One is array 1, the other one is array 2. Technically, both arrays should have equal elements. Sometimes you may have, one having one more elements than the other. And it's because, in the array, you can have even number or odd number of elements, right? So this is just an example, right? This example shows that array 1 actually have 5 elements, array 2 having 3 elements, but it doesn't really matter, okay? So the algorithm says this. It's basically everybody starting at, this location, okay, at 0 locations. And it's doing basically a pairwise comparisons, right? And said, hey, is this location greater than or less than that, right? If 1 is less than 2, then, hey, we move array 1 to final array. So there is a final array here, because what we want to do, this final array is going to have basically the combined length, right? So this got 5 here, 1, 2, 3, 4, 5, right? So this part is the length of this, right? The array 1 right there. You also have array 2. Array 2 has 3 elements, right? So this is not drawn to scale, by the way. So this part is the 2. So you have a total of 8 elements. So this is the final array. 8 elements is sitting in it, and you don't know what they are. So we need to insert 1 here, right? Because 1 is less than 2, right? So you can move 1 over, right? So basically, when that happens, then your next index becomes, right, on the array 1. So whichever one is it's got the elements inserted into the final array is the one that you have to index, basically increment its index. And then now you have basically 3, right? Index 1 here and index 0 still, because we haven't really moved anything from the array 2 yet. You do a comparisons, and 2 happens to be smaller than 3. Well, here, by the way, when we merge the 2 sorted array, we're assuming that we are sorting elements in the ascending order, okay? So here, you drop 2 here. And basically, because 2 is gone, right? Then you have to increment this index here on the array 2 to 4. So now, and this 1 is gone. So now you have 3 against 4, right? So on and so forth. So the algorithm is basically that, comparing every single element in array 1 against array 2 until either array is done, right? So in that case, everything else is just copied over, because you know that both arrays are sorted. So once you've gone through array 1 and array 2, you have basically total of n, right? So assuming that array 1 and 2, in this case, total of 8 elements here, O of 8. So this is an O of 8, O of n, right? Merging algorithms here. You cannot get more efficient than this, okay? You just can't. When you have 2 sorted array, you're doing a merge, O of n is the best you can do. So the actual merging problem is you cannot do this in place, okay? So meaning the left part is here, right part is here, and then because you start up with 2, right, arrays here. So what you need to do is, like I said, coming up with the final array right here. This final array is the one that you need to return, right? This is your final results. But initially, you don't have this populated. So what you need to do initially is to come up with either a fixed array that has total elements, right, size-wise of in array 1 and total number of elements in the array 2 size-wise, and do a combine and dynamically allocate sufficient temporary arrays to host that to the final array. So this is our solutions here. You have this temporary array, and then you do the algorithm as I state. Basically having this is your array 1, this is your array 2, right? Both are sorted, right? So there is an index here, right, that you have to keep track. There's also another index. So this is index number 1, and I just call it array 1 index, right? And here this is your array 2, right, index, right? So you're doing a comparison of the 2 to fetch their respective elements and see which one is smaller, and then you slot that smaller one, basically insert it into the temporary array, right? And then do a second one again, and then, right? So all this while you're doing, array 2 underscore index plus plus, and you're doing a plus plus on this side as well. Depends on which element, right? Which side of the element is being inserted into the final array. and so on and so forth until you're done, right? When either right indices reaches the end, right, then you can basically copy the remaining elements from the other array down because everything is sorted already, right? So together, you're basically touching every single element once, exactly once. So this is our solution. It calls for additional memory, spending, and this is unfortunate. There is nothing you can do to better this, right? Because the fact that merge sort requires O of n additional memory elements for the temporary array of the merge element. It is not exactly free, right? From a memory perspective. So you don't, at the same time, O of n might not seem a lot, but hey, if your, elements in the array is like several millions or billions, right? Then the amount of memory you need, in that case, is quite substantial because every element, assuming this is an integer, is 8 bytes, right? In Java, it could be another class instance that will call for a lot more, memory consumption. So this is the merge algorithms, right? As we stated earlier, while right there's more elements in left, and while there's more elements in right. Here's the left, here's right, and depends on their right which one is bigger, right? If the left one is bigger than the right one, then insert right the left one right in basically left one into it, and then increment left. And then or right if this is the other way around, that the right is actually greater right than your index on the elements on the right is more than the value on the left end, then you insert the right one right into the index. But you have to also increment the index. So this index is for the temporary arrays, right? So you have 3 indices: left first, right first, and then indices. There are 3 indices you have to keep track of, and this is O of n, right? As we say. So that said, this gives you right the merging algorithms, and it allows you to kind of merge both right sorted elements in there. Obviously, if left and right are not sorted, or either of them is not sorted, you don't want to do this, right? This merging algorithms only makes sense when you have both of them are in a correct order. So copy any remaining elements from left and right to temporary. So this is what I meant, right? Because the left and right are not right exactly. Sometimes they may not contain exactly the same number of elements. So if there is any remaining left right at the end of this while loop, what you do is you copy the remaining element from left to right. Actually, either the left to temporary or the right. So this is an OR, right? This is an OR. And then after you're done, right, you can copy the temporary array back into the value. So this is your entire buffer, or original buffer that you have, which was unsorted. Now it's going to have all of the elements inside of it sorted. You want to make use of the original buffer, but specifically whether you want to use the original buffer or not, it's really up to your applications. See if you're kind of needing the original buffer for future sorting application. So anyway, so this completes the merging the algorithm statement in the walkthrough. In the next video, we'll talk about merge sort, the actual sorting algorithms there that contributes to O of n log n. Okay, stay tuned.